Good morning, students. Today we are going to see very important principle which is used in the molecular orbital theory, linear combination of atomic orbitals, LCAO principle. Consider the two identical atoms like A1 and A2. These atoms having their atomic orbitals designated with wave function phi1 and phi2 respectively. When the atoms A1 and A2 form the bond, the electrons in atomic orbital A1 and A2 occupies low energy levels of molecular orbitals. Here, molecular orbital is formed by linear combination of atomic orbitals of wave functions phi1 and phi2, either by addition or subtraction of these two wave functions. See, after the addition or subtraction of these atomic orbitals, there is formation of the molecular orbital, which is represented by the wave function psi. So here equation is psi is equal to phi1 plus minus phi2, equation 1. Psi is the wave function of molecular orbital, while phi1 and phi2 are the wave functions of atomic orbitals of atom 1 and 2. For the better consideration of LCAO principle, let us consider the example of H2 molecule. Since H2 molecule is formed by the combination of two identical hydrogen atoms, so let us assume that phi1 and phi2 represent the wave function of atomic orbitals of 1s orbital of both hydrogen atoms. Here two possibilities of combining of wave functions phi1 and phi2 are given as: in first possibility, the wave function has similar phase for combination, that is plus sign, and second possibility of wave function has different phase of combination, that is minus sign. The sign means only orientation of atomic orbitals and do not means the symmetry of wave function. The wave function psi gives the possibility of finding the electron, and psi square gives the electron density. The wave function which are considered to be in phase, that having the same phase, they combine to give a cumulated wave function as given in figure. See, there are the two waves. In that particularly waves, similar part they will be combined, that is trubs, and we having the larger wave. So this combination of wave function of atomic orbitals have identical waves, that is in phase plus, and it gives the particularly addition of the waves. Similarly, the wave function with out of phase different sign which cancel the overlapping and gives rise to destructive interface, as see, there is the particular crust and trubs. Crust of first wave and trubs of second, they will be get combined, and in this combination we are having the wave function of atomic orbitals having different wave functions, which is the out of phase. From figure 1 and 2, which shows the probability of electron with the internuclear distance function. There are two ways of the combination of wave function. See, the first, psi g is equal to phi1 plus phi2. Here there is the addition of the waves. And second, psi u is equal to phi1 minus phi2. Equation 3. Here there is the subtraction of the wave. The summation of the wave functions and subtraction of the wave functions of an atomic orbital is termed as LCAO principle. The wave function psi u and psi g represent the molecular orbital form due to addition and subtraction of wave functions of atomic orbitals respectively. Letter G stands for the Girard, that is even, and letter U stands for un-Girard, that is odd. G and U are the symmetry notation of molecular orbitals. The wave function psi g leads to the increase in electron density between the nuclei, that is represents the bonding molecular orbital. The wave function psi u leads to decrease in the electron density or zero electron density between the nuclei, that is represent the antibonding molecular orbital. The antibonding molecular orbital ABMO is higher in energy and is indicated by the star, while bonding molecular orbital is lower in energy. The electron density in BMO psi g and ABMO psi u can be obtained by squaring the wave equation, that is equation 2 and 3. We get psi square is equal to phi 1 square plus phi 2 square plus twice phi 1 phi 2, equation 4. And in subtraction, psi square u is equal to phi 1 square plus phi 2 square minus twice phi 1 phi 2, equation 5. Equation 4 and 5 differs by twice phi 1 phi 2. The increase in electron density by an amount twice phi 1 phi 2 represents the BMO, and decrease in electron density by minus twice phi 1 phi 2 represents ABMO. Diagrammatic representation of the formation of BMO and ABMO. See, in the first diagram, there is addition of wave functions, there is addition of the orbitals wave function, and we have the particularly combine. It will be around the two nuclei of the molecule. See, in the second, they will be not combined, but they will be repelled, and bonding is not possible due to such combination. So it is the antibonding molecular orbitals. Rules for linear combination of atomic orbitals, LCAO. First, the addition of wave function of atomic orbitals to form the bonding molecular orbital may have the same sign. Second, the addition of wave function with opposite sign gives antibonding molecular orbital. Third, the number of molecular orbitals formed will be equal to the number of atomic orbitals combined. And fourth, atomic orbitals which do not have matching symmetry and energy for the combination, they form non-bonding molecular orbitals. There is difference between the BMO and ABMO, bonding molecular orbitals and antibonding molecular orbitals. So in BMO formed by the addition of wave functions of atomic orbitals, while ABMO formed by the subtraction of wave functions of atomic orbitals. BMO possesses lower energy than that of combining atomic orbitals, while ABMO possesses higher energy than that of the combining atomic orbitals. In BMO, electron density is concentrated between the nuclei. In ABMO, electron density is away from the internuclear region. BMO results in bonding, ABMO results in non-bonding. Nuclear repulsion is shielded, it is stable, and it has no node. Nuclear repulsion is not shielded, it is unstable, and it has, that is ABMO has a node perpendicular to internuclear axis. Now we are going to see the different combinations of atomic orbitals for the formation of the sigma and pi bonds. There are the SS combination, SP combination, PP combination, and PD combinations, and DD combination. So first we are going to see the combination of S orbital with S orbital, which is called as SS combination. Two atoms having the S atomic orbital leads to combine together to give sigma bond formation. This combination is also called as sigma molecular orbital. As see, there is the 1s orbital, 1s orbital, or s orbital plus s orbital. There is get combined, we get the bonding molecular orbitals, and in second there is the s orbital plus s orbital, but with opposite symmetry sign. It gives the antibonding molecular orbitals which have the node. So it is clearly indicated there. Then second, combination of s orbital and p orbitals, which is called as the sp overlapping. In this case, s orbital of one atom and p orbital of other atom, they will be get overlap and they get combined, which is called as the sp combination. This forms a sigma bond and hence molecular orbital is called as sigma molecular orbital. The combination of s and p orbital is represented here in the figure. See, s orbital plus there is the px orbital along the internuclear axis, they will be combined and gives the sigma bonding molecular orbital. In second, there is the s orbital and p orbital, they will be get combined, but there is a node between the atoms, and thus we having the bonding molecular orbitals and the anti-bonding molecular orbitals, but one is the sigma bonding molecular orbital and second one is the sigma anti-bonding molecular orbital. See, there is the pp combination. The p orbital of the first atom and p orbital of the second atom, they will get combined, which is called as the pp combination. In pp combination, there is the sigma as well as the pi bond. See, first there is the formation of the sigma bond, pp combination for the sigma bond. Here there is the along the internuclear axis px orbital and px orbital, they will be combined and we get the sigma BMO. While when there is the symmetry notations are the different and when they will be combined, there is a node between them and we can get the sigma ABMO. Thus sigma BMO and sigma ABMO. Second type, which will be gives us the pi bonding. See, pp combination for pi molecular orbitals. See here, there is the py orbital of the first atom and py orbital of the second atom. Symmetry notations are at the particularly one side, same symmetry notations at one side, and thus we having the particularly electron density or their combination is perpendicular to that axis, and we having the pi BMO and pi ABMO. See, in the second figure, there is the particularly lateral overlapping, and with the different notation, we having the antibonding molecular orbitals. Third, that is the PD combination. P orbital of the first atom and D orbital of the second atom, they will get combined, and from this we can have the pi overlap bonding molecular orbitals and pi overlapping antibonding molecular orbitals. Here there is the pi bonding is possible, and thus we can get the pi BMO and pi ABMO, which are the perpendicular overlapping or the perpendicular combination along the internuclear axis. The DD combination, DD atomic orbitals, they will be get combined and they can give the particularly delta orbitals. That delta orbitals here on the two-dimensional, it is not shown here. Difference between the sigma and pi molecular orbitals. See, sigma molecular orbitals and pi molecular orbitals. Sigma MOs formed by the overlapping and combination of atomic orbitals pointing their lobes along the internuclear axis, while pi molecular orbitals formed by overlapping and combination of atomic orbitals which having the lobes perpendicular to the internuclear axis. BMO sigma molecular orbital results in the electron density concentration between the two nuclei, while pi molecular orbital electron density is 0 between the two nuclei. It is perpendicular to the internuclear axis. All sigma BMOs are symmetrical and all sigma ABMOs are unsymmetrical. Here there is no symmetry for the pi BMO and pi ABMO.